For decades, Europa seemed like a pristine, frozen wasteland, a smooth ball of ice orbiting Jupiter, beautiful in photographs, yet unremarkable in ways that truly mattered. Scientists discussed it with polite detachment, like admiring a colleague's vacation photos. Nice. Interesting. Moving on. But beneath that seemingly inert white shell, something extraordinary has been stirring. Something warm. Something active. Something that defies expectations for a moon so small, so cold, and so distant from the sun. In the last 18 months, the James Webb Space Telescope has methodically, quietly, peeled back the layers, revealing Europa's true nature. What it discovered was not what anyone predicted, and it's a revelation that could redefine our search for life beyond Earth. To truly grasp the significance of these findings, let's revisit what we thought we knew, for that is where the most profound shifts have occurred. Europa, one of Jupiter's 4 Galilean moons, was first observed by Galileo himself in 1610. Slightly smaller than our own moon, it spans approximately 3,100 kilometers. From space, its surface resembles a cracked eggshell, composed almost entirely of water ice, adorned with reddish-brown streaks and ridges extending for thousands of kilometers. Crucially, beneath this icy exterior lies a vast ocean. Our suspicion of this began in the late 1990s, when NASA's Galileo spacecraft detected anomalies in Jupiter's magnetic field near Europa. These disturbances could only be explained by a massive, electrically conductive liquid body beneath the moon's surface, salt water. An entire ocean of it, likely holding more water than all of Earth's oceans combined, sealed under an ice shell estimated to be between 10 and 30 kilometers thick. This subsurface ocean is what propelled Europa into the spotlight. The presence of liquid water, anywhere, immediately raises the possibility of life. Not a certainty, not even a strong indication, but simply a door left ajar. For 2 decades, that partially open door was all we had. We couldn't pierce the ice, couldn't sample the water, couldn't analyze its dissolved contents, or determine if any biological processes were occurring deep within. We were, in essence, peering through frosted glass from the outside. The James Webb Space Telescope fundamentally altered this. It didn't achieve this by drilling through the ice or deploying a lander, but by a deceptively simple yet revolutionary act, intently observing Europa's surface with the most sensitive infrared instruments ever constructed, and meticulously deciphering the chemical fingerprints of its composition. In September 2023, 2 independent research teams unveiled their findings from Webb's near-infrared spectrograph, an instrument so exquisitely precise it can identify molecules on a surface over 600 million kilometers distant. Their primary target was carbon dioxide, not because carbon dioxide is inherently thrilling, but because of its profound implications. On Europa's surface, carbon dioxide could originate from 2 distinct sources. It might be delivered by meteorite impacts or radiation from space, external factors unrelated to the subsurface ocean. Alternatively, it could emanate from within, from the ocean itself, propelled upwards through fissures in the ice and deposited on the surface. If the carbon dioxide proved to be internal, it would unequivocally signify the presence of carbon within the ocean. And carbon, as we know, forms the fundamental backbone of all known life. Both teams found it. Carbon dioxide, heavily concentrated in a specific area known as Terra Regio. This region is a geologically young expanse of disrupted terrain, situated on Europa's trailing hemisphere. This wasn't a mere dusting of carbon dioxide randomly scattered by meteorites. It was concentrated, localized, and found precisely in the type of terrain that geological models predict would be replenished by material rising from below. The distinct distribution pattern unequivocally pointed downwards, towards the ocean. Geronimo Villanueva, lead author of one of the studies and a planetary scientist at NASA's Goddard Space Flight Center, articulated it clearly. The carbon dioxide was not arriving from outside. It was consistent with an internal origin. This means Europa's subsurface ocean contains dissolved carbon dioxide, and the geological activity of Terra Regio has brought traces of it to the surface, much like a stain seeping through fabric. The presence of carbon in a subsurface ocean is a fundamental prerequisite for the type of chemistry that could, theoretically, sustain life as we know it. But Webb's revelations didn't stop there. In March 2024, another team utilized Webb to investigate plume activity, jets of water vapor erupting from Europa's surface into space. The Hubble Space Telescope had previously reported potential plumes in 2012 and again in 2016, but these detections were tentative, pushing the very limits of Hubble's capabilities. While some scientists were convinced, others remained skeptical. Webb's observations, however, provided a clearer picture. No large, persistent plumes were detected during its observation window. While this might initially sound like a setback, it is far from it. This finding suggests that Europa's plume activity, if it occurs, is likely sporadic rather than continuous. Unlike Enceladus, Saturn's small moon, which continuously erupts geysers from its south pole, driven by tidal forces kneading its interior like dough, Europa seems different. Its outbursts, when they do happen, are intermittent, possibly triggered by specific tidal stresses as Jupiter's immense gravity flexes the moon's ice shell during its orbit. So, what powers this hidden ocean? Europa is incredibly distant from the Sun, making solar heating negligible at Jupiter's orbit, approximately 780 million kilometers away. The surface temperature hovers around a frigid 160 degrees Celsius. By all superficial measures, this moon should be frozen solid throughout. The answer lies with Jupiter itself. Europa's orbit is not perfectly circular. It is slightly elliptical, shaped by the gravitational dance between Jupiter and its other large moons, particularly Io and Ganymede. As Europa alternately approaches and recedes from Jupiter during each orbit, the planet's immense gravity rhythmically squeezes and stretches the moon's interior. This phenomenon, known as tidal heating, is the same mechanism that makes Io the most volcanically active body in our solar system. On Europa, the effect is more subtle, yet still potent enough to maintain a liquid ocean for billions of years beneath kilometers of ice. Imagine rapidly flexing a rubber ball in your hands. It quickly warms up. Now, picture that ball being 3,100 kilometers wide, and the hands compressing it, belonging to the largest planet in the solar system. The immense energy generated by this constant flexing doesn't just sustain liquid water. It could also drive hydrothermal activity on the ocean floor, creating hot vents where mineral-rich water mixes with the cold ocean. This is precisely the kind of environment where life on Earth is believed to have originated nearly 4 billion years ago. Current estimates suggest Europa's ocean could be between 60 and 150 kilometers deep. To put that into perspective, the deepest point in Earth's oceans, the Mariana Trench, reaches approximately 11 kilometers. Europa's ocean, contained within a moon smaller than our own, could be more than 10 times deeper. At the bottom of this immense body of water lies a rocky, silicate floor, not a layer of high-pressure ice as found within Ganymede. The direct contact of rock with liquid water is crucial, as rock is the source of essential minerals, the very starting point for complex chemistry. Webb's discovery of carbon dioxide fits perfectly into this emerging picture. If the ocean floor is hydrothermally active, and the ocean contains dissolved carbon and other compounds, then Europa possesses 3 of the 4 ingredients astrobiologists deem necessary for life: liquid water, energy, and chemistry. The 4th ingredient is time, and Europa has had an abundance of that. Its ocean is estimated to have existed for billions of years. It is vital to emphasize that none of this conclusively proves the existence of life on Europa. We must be cautious. Detecting carbon dioxide on the surface of an icy moon is a far cry from discovering a microbe. The chasm between conditions that could support life and conditions that actually produced life is vast. Furthermore, we possess only one data point for how life originates: Earth. Drawing definitive conclusions from a sample size of 1 is inherently flawed science, regardless of how thrilling the results may appear. What Webb has achieved is a significant narrowing of possibilities. Prior to these observations, we understood Europa had liquid water and an energy source. Now, we know it also possesses carbon. Each confirmed ingredient progressively diminishes the arguments against the potential for life to exist there. There's another crucial aspect of Webb's data that, while receiving less public attention, holds immense significance for future exploration. The research teams also actively searched for organic molecules, complex, carbon-based compounds that form the foundational building blocks of biological chemistry. The results, however, were inconclusive. Webb detected tantalizing hints of something, but the spectral signatures overlapped with other potential compounds, rendering a definitive identification impossible from such a vast distance. This ambiguity is not a failure. Rather, it serves as a critical signpost, directly indicating what the next generation of instruments must now focus on finding. NASA's Europa Clipper mission, launched in October 2024, is now en route, carrying the most sophisticated array of instruments ever dispatched to the outer solar system. Over approximately 50 close flybys of Europa, some venturing within just 25 kilometers of its surface, Clipper will meticulously map the ice shell, measure its thickness, actively search for plumes, analyze the composition of any ejected material, and probe the ocean's depth and salinity using advanced radar and magnetometry. If Terra Regio is indeed leaking oceanic material to the surface, Clipper will effectively taste it. If organic compounds are embedded within the ice, Clipper's mass spectrometer will definitively identify them. While Clipper won't reach Jupiter until 2030, Webb's carbon dioxide discovery has critically refined its target list. Terra Regio, already a region of interest, has now become a paramount priority. The combination of its disrupted terrain, the carbon signature, and the geological youth of its surface all strongly indicate a location where the ocean actively communicates with the surface. Clipper's mission is to listen to this communication at close range and meticulously decode its message. And Clipper will have to operate with remarkable speed. Jupiter's intense radiation belt bombards Europa with approximately 540 rem per day, a dose lethal enough to kill an unshielded human within hours. To withstand this hostile environment, Clipper's sensitive electronics are housed within a titanium vault with walls nearly a centimeter thick. Even with this formidable armor, the spacecraft can only endure brief passes near the surface before retreating to safer distances. This is why the mission involves 50 flybys instead of a stable orbit. Parking a spacecraft at Europa would inevitably fry its instruments within mere weeks. Among Clipper's 9 sophisticated instruments is SUDA, the Surface Dust Analyzer. Its critical task is to capture and analyze microscopic grains of ice and dust ejected from Europa's surface by micrometeorite impacts or potential plume activity. Each such grain is, in essence, a tiny frozen sample of the material residing on or just beneath the surface. SUDA possesses the capability to determine the molecular composition of individual grains, meaning it doesn't require a dramatic eruption to gather invaluable data. Even the subtle haze of particles dislodged by routine surface impacts is sufficient. A single grain caught by this instrument could fundamentally alter our understanding of Europa's ocean. Clipper is also equipped with an ice-penetrating radar named Reason, designed to map the internal structure of the ice shell to a depth of approximately 30 kilometers. For years, theoretical models have posited the existence of liquid water pockets trapped within the ice shell itself, nestled between the frozen surface and the deep ocean below. If these lakes exist, Reason should detect them as bright radar reflections at shallow depths. Their discovery would imply that Europa's potentially habitable volume isn't confined solely to the deep ocean. Instead, there could be water reservoirs relatively close to the surface, potentially more accessible for future landers. The chaotic terrain, which covers roughly a quarter of Europa's surface, regions where immense ice blocks have been jumbled, tilted, and refrozen at bizarre angles, has long been interpreted as compelling evidence of subsurface activity destabilizing the ice from beneath. The theory suggests that warm ice or liquid water rises from deep within, softening the overlying ice, causing the surface to collapse and refreeze in a disordered state. If this model holds true, then the carbon dioxide Webb detected at Terra Regio was transported relatively quickly upwards by a convective process, cycling ocean chemistry towards the surface in geological bursts. This paints a picture of a moon with an active internal circulation system, a moon that is, in a very real sense, geologically alive, even if not biologically. The intense radiation environment around Europa introduces another layer of complexity, and it cuts both ways. Jupiter relentlessly bombards Europa's surface with powerful radiation, charged particles accelerated by the planet's enormous magnetic field, This radiation is potent enough to destroy complex organic molecules on the surface within mere decades. Any biosignature that might reach the surface from the subsurface ocean would likely be fragmented and obliterated before we could detect it from orbit. However, this same radiation also breaks apart water ice and other surface molecules into fragments that then recombine into new compounds, including hydrogen peroxide and molecular oxygen. Some scientific models propose that this radiation-produced oxygen could be cycled back down through the ice into the ocean below, where it would become available as a chemical energy source for any organisms that might potentially exist there. In an astonishing paradox, Jupiter's radiation, which sterilizes the surface, might simultaneously be providing sustenance for the ocean. When I first learned about this feedback loop, it truly gave me pause. A giant planet showering its moon with lethal radiation, and that very radiation, filtered through 30 kilometers of ice, potentially arriving at the ocean as a source of food. Europa clearly does not operate by intuitive rules, and Europa continues to deliver surprises beyond the carbon dioxide narrative. In late 2024, further Webb observations unveiled crystalline water ice features on Europa's surface that appeared remarkably fresh. The presence of fresh ice on a moon constantly bombarded by radiation strongly suggests recent resurfacing, material from below actively replacing the irradiated surface layer. Crucially, the distribution of this fresh ice correlates precisely with the same disrupted terrain where the carbon dioxide was discovered. Whatever geological processes are occurring beneath the ice are evidently still ongoing. The chemistry Webb detected isn't a fossilized record, it's a current bulletin. Upon closer examination of the spectral data, researchers discovered that the carbon dioxide was intermingled with other salts, specifically sodium chloride and magnesium sulfate, essentially table salt and Epsom salt. These are the same types of salts dissolved in Earth's oceans. Their presence in the same regions as the carbon dioxide vividly illustrates a system in active communication. The ocean communicates with the ice. The ice, in turn, eventually communicates with the surface, and the surface, bathed in Jupiter's radiation, communicates with space. Webb essentially intercepted this conversation mid-sentence. The composition of these salts also provides critical input for models assessing the ocean's habitability. On Earth, hydrothermal vents on the ocean floor generate specific ratios of dissolved minerals, influenced by the temperature and chemistry of the rock they interact with. If Clipper can precisely measure the salt ratios on Europa's surface and correlate them with the seafloor conditions predicted by tidal heating models, scientists will gain the ability to estimate the temperature and chemical environment of the ocean floor without ever directly sampling it. They will, in effect, be reading the ocean's diary from its outside cover. Concurrently, the European Space Agency's JWST mission, launched in April 2023, is on a more gradual trajectory to the Jupiter system. While JWST will primarily focus on Ganymede, it will also perform 2 flybys of Europa. Its instrument suite is complementary to Clipper's, ensuring that the 2 missions can cross-reference and validate each other's data. In the realm of planetary science, such redundancy is not a waste. It is vital insurance against the kind of ambiguity that hindered the earlier Hubble plume detections. There's a profound philosophical weight to all of this, that I believe often gets overshadowed by the technical intricacies. For the majority of human history, the question of whether life exists beyond Earth was relegated to the domains of theologians and philosophers. It wasn't a scientific inquiry, because we simply lacked the tools to investigate it. Then, we constructed telescopes, we dispatched probes, we landed on Mars only to discover a cold, barren desert. We mapped Venus and found a searing furnace. We cataloged the moons of the outer planets, mostly revealing cratered, airless rocks. Slowly, almost imperceptibly, the fundamental question shifted from philosophy to chemistry. It was no longer, is there life out there, but rather, are the ingredients for life present? That is a question one can answer with a spectrograph, and that is precisely the question Webb is answering for us right now. I consistently return to Terra Regio because it stands as the geographic centerpiece of all that Webb has revealed. It is, geologically speaking, a relatively young region. Its surface has been extensively reworked, broken apart, and reassembled by powerful forces originating from below. The carbon dioxide discovered there sits like a distinct fingerprint left by the ocean, pressed into the ice by the upwelling processes that continually reshape this terrain. If one were to design a landing site for a future Europa lander, a mission that could one day drill through the ice and directly sample what lies beneath, Terra Regio would undoubtedly be at the top of the list. Webb has, quite literally, drawn an X on the map. If you could somehow stand on Europa's surface and gaze upwards, the sky would be utterly dominated by Jupiter. Not a distant dot, not merely a bright star, but an immense banded wall of swirling gas. Jupiter would fill nearly 24 degrees of the sky, approximately 48 times the apparent size of our own full moon as seen from Earth. It would hang there, a majestic sphere banded in oranges, browns, and whites, slowly rotating, with the great red spot perpetually drifting across its face like a bruise that never heals. In that moment, you would comprehend, in a way no photograph can truly convey, just how small Europa is, and how completely its existence is at the mercy of that enormous planet. The powerful tides that keep its ocean liquid, the relentless radiation that sterilizes its surface, the gravitational resonance that locks its orbit, all emanate from Jupiter. Europa does not exist independently. It exists because Jupiter permits it to. And the very conditions that make its ocean possible are the same conditions that render its surface lethal. This inherent tension is the defining characteristic of this moon's existence. What has genuinely and measurably changed because of the James Webb Space Telescope is the sheer strength of Europa's case. Before 2023, Europa was considered a promising candidate in the search for habitable environments beyond Earth. Now, after Webb's definitive carbon dioxide detection, after the confirmation that the ocean's chemistry is indeed reaching the surface, after the refined understanding of plume activity, and with sharpened target maps for Clipper, Europa has transitioned from merely promising to undeniably compelling. The distinction between those two words represents the shift from a theoretical hypothesis to a robust, active research program. We now possess specific, testable predictions about what Clipper should uncover upon its arrival in 2030. We have a named location where oceanic material appears to be accessible, and we have a chemical ingredient list that continues to expand. Somewhere within that profound tension, in the chasm between a surface that relentlessly destroys organic molecules and an ocean that might be actively producing them, there could lie the answer to the oldest question our species has ever posed. What would we truly discover if we could actually obtain a sample of that ocean water? Not merely infer its composition from surface deposits, nor model it from orbital data, but physically scoop up a vial of Europa's ocean and analyze it in a laboratory. If we were to find amino acids, lipids, or any of the molecular signatures that life produces on Earth, even in the absence of cells, even without anything recognizably alive, it would represent the most consequential discovery in the history of science. Not because it would definitively prove life exists on Europa, but because it would demonstrate that the chemistry of life is not unique to Earth, that the universe generates these fundamental building blocks wherever the conditions permit, thereby proving that we are not an isolated fluke. Europa never demanded our attention. It didn't dramatically erupt like Io, nor did it flaunt its lakes and rivers openly like Titan. Instead, it meticulously guarded its secrets beneath 30 kilometers of ice, leaving us to speculate. For 2 decades, we did just that. We guessed. Then, Webb turned its gaze, carefully, patiently, with instruments engineered for precisely this kind of subtlety, and Europa finally offered us something tangible. The ice has not yet cracked open for us, but Clipper will venture closer than any spacecraft we have ever dispatched. Suda will capture ice grains no larger than a grain of sand and read them like ancient letters from the deep. And one day, perhaps in the 2040s, or even later, a dedicated lander will touch down on that fractured terrain, melt its way through the ice, and deploy an instrument into water that has never known sunlight. Whatever it discovers down there, be it barren salt water or something far stranger, will fundamentally rewrite our understanding of where life can exist in the universe. For now, we wait. But for the first time, we are waiting armed with compelling evidence, not merely with hope.